Welcome back to Mixtures and Solutions. We left off talking about solutions and we were about to move into talking about solubility. So let's begin. First, I want to talk about types of solutions. So we have gas solutions, liquid solutions, and with the gas solutions, we have two or more gases. Pretty simple, self-explanatory. Liquid solutions involve liquid solvent with gas, liquid, or solid as the solute. So this brings us to the concept of miscibility. Miscibility means that they will or will not dissolve completely. So if something is miscible, that means we have two liquids that will dissolve completely in one another. Alcohol with water, they completely dissolve. Things that are immiscible will not dissolve or may not completely dissolve. So here we're talking about oil and water, for example. Some ionic compounds don't dissolve well, so we would classify them as insoluble or immiscible. Then we get to our solid solutions. This is where we have a mixture of solids that are uniformly spread throughout one another. And this is at the atomic or the molecular level. So here we're talking again about steel or other types of solid solutions, mercury amalgams, metal mixtures, 24 karat gold, for example. Those are all solid solutions. Alloys, again, solid solution. So now let's talk about solvation, the process of dissolving. That's literally the definition. So first, we have solute particles that get surrounded by solvent particles. And then those solvent particles then basically pull the solute particles into solution. The solvent particles get in between the particles of the solute, causing them to move into solution and dissolve. This is our process of solvation, or process of dissolving. So here's an example of a dissolving ionic crystal. The red and white molecules, those are water. The green and blue is representing some sort of a ionic crystal, an ionic crystal, excuse me. So what we see here are the water molecules getting in between and kind of pulling apart and separating out, interfering with the ionic interaction between the particles of the compound to pull them apart. The concept here is what's known as dissociation. So this is what's going on with solid ionic compounds that are dissolving. Here we have an ionic solid that dissolves because it ends up being pulled apart because the water molecules have this force of attraction, and they kind of interfere with the interactions going on between in this case, the sodium and the chlorine atoms. So the sodium and chloride ions, excuse me. So you have sodium and chloride ions, and they're typically very highly attracted to one another, but when water comes in between them, they separate apart. And they're surrounded by water. Each one of them gets surrounded by water. So we have two aqueous ions in solution. This is because sodium chloride and many other ionic compounds completely dissociate. They completely break apart because the water interferes with their interaction between the ions. If we have polar molecules like an acid, and they break apart because they're dissolved in solution, we end up with what we call ionization. So ionic compounds dissociate while polar molecules will ionize. And so we get hydrogen ions and nitrate ions when we take nitric acid and we dissolve that in water. Then we get molecular solvation. Here it's like we have this cube that has, let's just consider it a sugar cube. And the sugar cube, the water molecules come in between the separate molecules of sugar that are essentially like they're stacked in this crystalline structure. And so the water molecules basically just come in between the separate molecules. Instead of coming in between the ions, or instead of breaking them apart into ions, they just interfere with the intermolecular forces, the forces between the molecules. And this causes the molecules to break apart, or the molecular, the molecular matrix of this larger structure to break apart to separate the individual molecules apart from this mass globular structure of molecules. One thing that's really important to understand when it comes to dissolving is that polar things will dissolve in other polar things. Ionic things will dissolve in certain polar things, but non-polar things will not dissolve in polar stuff. This comes down to a concept that we like to refer to as like dissolves like. Polar compounds like to interfere with ionic compounds, and they like to interfere with polar compounds. But they don't do well getting in between the molecules of nonpolar compounds. Whereas other nonpolar compounds can do a great job sometimes of getting in between other nonpolar compounds. So if we take something nonpolar, so oil, for example. Oil is a classic example of a nonpolar substance. And I put that with water. We all know what happens when oil and water are mixed together. They don't dissolve in each other. They're not miscible into each other. Oil and water are immiscible because they are not similar in polarity. Water is polar. Oil is nonpolar. But if I take oil and I dissolve it, or I put it into a solution of carbon tetrachloride, a completely nonpolar substance, the oil will dissolve in the CCl4. And we will have a solution of CCl4 with the nonpolar oil. Polar things will dissolve in other polar things. So alcohol is an organic compound, but it's a polar compound, which means, if you remember, we have partial positive and partial negative going on. Water is also polar, which has partial positive and partial negative ends of the molecule. And so if I put something with partial positive and partial negative ends on a molecule into something else that has partial positive and partial negative ends on its molecules, they will be attracted to one another and they will interact, thereby dissolving. So, polar and polar, like dissolves like. Nonpolar and nonpolar, like dissolves like. But nonpolar and polar doesn't work out. Another example here, like it shows up here on your screen, is sodium chloride is ionic, meaning that it has positive and negative charges, similar to the way that polar compound or polar molecules interact or are involved. Now, benzene is completely nonpolar. And so if I take benzene and I take sodium chloride and I put them together, the sodium chloride, that salt, will not dissolve in the benzene. Here we got oil and water, crude oil with water. It just does not mix together. They will not dissolve. We have a heterogeneous solution, or mixture, a heterogeneous mixture, while we don't have a solution because the oil will not dissolve in the water because oil is nonpolar. So when it comes to solubility, if two substances are similar enough, we can determine their solubility by looking at the maximum grams of solute that are going to dissolve in 100 grams of solvent at a given temperature. This is our definition of solubility, when two things will be miscible. So we can have ionic compounds that at a certain temperature have very, very, very low solubilities in water, whereas at a high temperature they have a great solubility in water. So solubility. When we have a solution that holds or contains all the solute that it can have at a specific temperature, we refer to that solution as being saturated. So if we're dealing with a solution at 20 degrees Celsius and we put 34.7 grams of potassium chloride in 100 grams of water. That is as much potassium chloride that can be dissolved in that water, in 100 grams of water, at 20 degrees Celsius. If we add more, all that's going to happen is the potassium chloride, the extra is going to just settle down to the bottom. It won't go into solution. But if we change certain properties of the solution, we might be able to get more to dissolve. So we had saturated. Now we also have unsaturated, which is on the low end, and we have supersaturated, which is on the high end. So an unsaturated solution is when we have less solvent than can be held at that temperature by the solvent. Less solute than the solvent can hold at that temperature. I don't know what I just said a moment ago, but I feel that it wasn't what I needed to say. So we have less solute than can be held by the solvent at that temperature. That is an unsaturated solution. That means we can dissolve more. But if we take a solution that we have saturated and we heat it up and we add more solute to it, the excess solute doesn't just fall down to the bottom. It may be able to continue dissolving. Now, not all salts will do this, but some of them will. And when we slowly cool it back down, we might not end up with it staying, or excuse me, falling out of solution or precipitating out or crystallizing. In this case, we have what's called a supersaturated solution. But if we add what's referred to as a nucleation site, something that a crystal can form on, then suddenly crystallization is going to start happening and we get precipitation of that substance. If you've ever seen a reusable hand warmer, this is a great example of a supersaturated solution. And you can make your own, believe it or not. You can take sodium acetate and we take that and we make a supersaturated solution. Technically, we could even do it with sodium chloride if we wanted to. But these reusable hand warmers that you can buy have sodium acetate in them. And they are a supersaturated solution. And when you pop the little coin-looking thing inside, you create a nucleation site, a spot where it's almost like a grain of sand is suddenly introduced into the solution. And when you do that, it allows for all these crystals to start forming. But in the process of them forming, it's extremely exothermic. Well, not extremely, but it is exothermic. And when it's exothermic, that means it releases heat. So heat energy gets released, and that's what gives it that warm feeling that allows you to use it as a hand warmer. But if you take it and you put it into a pot of boiling water, and you allow those particles to dissolve again, bring it back out, and slowly let it cool back down to room temperature, then you have the hand warmer to use again. So, an unsaturated solution, we can dissolve more into it. A saturated solution can't dissolve any more into it at that temperature. But if we raise the temperature enough, we might be able to. And if we do that, we get a supersaturated solution. But supersaturated solutions are unstable. This means that if we add something to allow nucleation, I keep referring to this nucleation sites and nucleation. This is just, it's a particle for something to latch on to start solidifying. We get crystals that start forming. So we have three fundamental factors that affect how much of something will dissolve. The first is the nature of the solute and solvent. Here we're talking about their characteristics of being polar versus nonpolar. Temperature is the second key factor. So the first one really tells us, is it even possible for these things to interact enough to dissolve? The second one, if we have a higher temperature, there might be the ability for us to add more or just for it to dissolve. So generally, solubility increases as we increase temperature. Stuff that may not dissolve at lower temperatures may dissolve a little bit better if we just raise the temperature enough. Gases, though, work a little differently. So with solids, that's what I was referring to a minute ago. Solids, generally, we increase the solubility as the temperature increases, but with gases, it works the other way. If we increase the temperature, it becomes less able to dissolve. This is an example of a solubility curve. A solubility curve has two axes, and it's a graph. Okay, so on the x-axis, we're looking at temperature, and on the y-axis, we're looking at the ability to dissolve. In this form, it's in millimoles per liter at 1 atmosphere of pressure. So if we're dealing with carbon dioxide, it is best dissolved at lower temperatures. As we increase temperatures, those particles are so excited, they're so full of kinetic energy that they're less able to be kept still long enough or to be kept in place to dissolve into something. They just jump right back out. Now, xenon works the same way. Nitrogen, again, works that way. These are all gases. Oxygen, again, less soluble with increased temperature. But carbon dioxide is kind of the most extreme example that we have here. On the left, though, we have our solids. And we see as increasing temperature happens, there's really only one substance that we can see on this graph that will decrease in solubility with increased temperature, and that is lithium sulfate. So the higher temperature, lithium sulfate is kind of this outlier. It dissolves less frequently or less well, dissolves poorer at greater temperatures. But all other solids that we have in this graph are dissolving much better at higher temperatures. This is because of the energy involved in the movement of the particles that we're dealing with. Increasing the temperature increases the energy. They receive thermal energy and it transfers into kinetic energy, and these particles are vibrating much faster, and as they increase their movements, they end up potentially moving just enough to break apart. So then our third key factor, or fundamental factor that affects solubility, is pressure. With gases, if we increase the pressure on it just enough, we might be able to get it to dissolve. So for gases, if we increase pressure, we increase solubility. Changing in pressure with solids and liquids really doesn't have much effect, but gases, it has a great effect. So then we move into what affects how quickly things dissolve. So we have the ability to dissolve, that's solubility. But now we have rate of solution, how fast something's going to dissolve. And this is determined by the quantity of solute that will dissolve during 1 unit of time, whether that time's seconds or minutes or milliseconds or hours or days or what it is. But the factors that affect rate of solvation, or rate of solution, include the size of the particles. So if we're dealing with a large particle, we're dealing with something that doesn't have a lot of surface area to work with. So if we break that up into lots of smaller particles, then we have more surface area for interaction with the solvent. This allows for faster solution to occur, faster dissolving. Another factor is stirring. If we stir it, we increase the kinetic energy of the molecules involved, and we bring fresh portions of the solvent into contact with the solute, or fresh portions of solute in contact with the solvent. Either way, we're seeing more interaction happening between solvent and solute. And when you increase the ability of the interaction to happen, or the time in which interaction is happening, you're able to increase the solution's rate of happening, or the rate of something being dissolved. And then we have the last factor, which is the amount of solute that's already dissolved. If we don't have a lot of solute already dissolved, then things might dissolve pretty quickly. But if we've got a lot of stuff already dissolved in there, the water molecules are pretty busy dealing with the presence of everything else. Those polar molecules are just interacting like crazy. They are social butterflies. But you add more to it and they begin to get to the point where they just kind of get overwhelmed and they can't get to everybody all at once. It's kind of like a teacher. If I get 10 students asking me questions, I'm good. But once that increases to 100 students, if I go by tenfold and increase to 100 students, then I start struggling, and some students end up going without their questions being answered. It's not fair to those students. But it's a similar example to what goes on if we have a lot of particles already dissolved. There's already a lot of interaction happening with the solvent molecules, and so there's not enough to spare to interact with the others of the solute particles. Fourth, we have temperature. Increasing temperature not only increases solubility of solids, but it increases the rate at which solids and liquids will dissolve. It's the exact opposite for gases, though. Gases do the same thing that they did before with temperature. Not only do they decrease in their solubility, but they decrease in how quickly they'll dissolve. I hope that's kind of self-explanatory. If it's not, let me know, and I will help.